So let's go through an example of Hardy-Weinberg equilibrium equations. So this is a real-life disorder called phenylketonuria, and it's a mutation that in humans that causes you to be unable to process the amino acid phenylalanine. So this is it's pretty rare. But what happens is the phenylalanine builds up in the body and you're not able to get rid of it, and it can cause serious damage. Typically, babies who have this are screened in the United States. It's something that's avoidable, not avoidable, but you could avoid symptoms by avoiding foods with phenylalanine in them. Okay, so we've got 5 conditions of Hardy-Weinberg equilibrium, and the first one is no mutation. This gene is really rare. The mutation isn't 0, but it's really low, so we can just say it's close enough. So random mating. People don't typically know about PKU, so PKU isn't something that presents physically unless you've got symptoms from it. But typically with avoiding foods that have phenylalanine, you're not going to present symptoms. So people aren't going to choose mates based on whether or not they have phenylketonuria. Natural selection is pretty rare because it's only going to act on individuals that are homozygous recessive, and then also who don't follow the dietary restrictions. So in today's world, you can be affected by this, but still not selected against because you can follow other dietary restrictions. The population of the United States is sufficiently large, and gene flow is not really an issue because other populations in other countries like Mexico, Canada, are going to have similar rates of this allele already. So even if they're coming into the country, even if they're leaving, most often it's not really going to affect the rate of PKU. So this one specific gene, it's not perfect, but it mostly fits the 5 conditions of the Hardy-Weinberg equilibrium. So the occurrence of PKU is 1 in every 10,000 births in the United States. So what this means is that this is going to be 0.0001 number of chance of being born with PKU. PKU is homozygous recessive, so if we've got A and little a, somebody with PKU is going to be little a. That'll be their genotype. So our Q squared is the frequency of this genotype, right? Well, that we just determined was 1 in every 10,000. So here's my frequency. It's 0.0001 births. So from Q squared, that's all I have. What I want to do is I want to figure out the rest of these variables. From Q squared, I can figure out Q. All I need to do for Q squared to figure out Q is just take the square root. So when I take the square root of this, I get Q is equal to 0.01. Now that I have Q, I can figure out P. Remember that P plus Q equals 1. So now I know that P plus 0.01 equals 1. Subtract 0.01, subtract 0.01. P is going to be equal to 0.99. So the dominant alleles are P. P is equal to 0.99. Alright, so let's figure out the frequency of carriers. So carriers are somebody who is going to be big A, little a. So we know that this is 2PQ. Well, we already have P and we already have Q, so we can go ahead and figure this out. So 2 times 0.01, which is Q, times 0.99, which is P, is going to equal 0.0198, which is approximately, let's move this over to 2% of the population are carriers for this disease. So we only have 4 out of our 5 variables. We have almost all of them. We have Q squared, Q, P, and 2PQ. The last one that we're missing would be P squared, which is going to be homozygous dominant. These are people who are just normal and not carriers. And because we already have P, we can just figure this out. So P squared is equal to 0.99 times 0.99. And that's equal to 0.9801, which, scrooched over, is approximately 98%. Obviously, I'm approximating. This is about 0.01%. So very, very small amount of the population actually has PKU. A little bit larger is a carrier for it, and the vast majority are going to be normal. And we can look at this over time and see if the population is evolving by seeing if these numbers change over time.